First we will see like introduction. Introduction means we will see like linear versus non-linear. Okay. Then uh, we will see this Newton-Raphson method. Okay. So before this, we'll just yeah, I think this is fine. First, we need to discuss Newton-Raphson. Then we will see geometric nonlinearity. Okay. So we will discuss this geometric nonlinearity here as well. Okay, in this linear versus nonlinear. But we will here we will see more like no, examples and possible demos. Okay, and possibly demos. Okay. So uh, yeah, here we will try to understand this with 1D bar element. 1D bar element as usual. Okay. So we'll see with no hand calculations. So then we will also see this convergence tolerances. Okay, this actually will be part of this only. Okay, so convergence tolerances, or you would have heard about convergence criteria. Okay, so we will see that, and yeah, that's it. So let's start with the linear versus non-linear. Okay, let's see linear versus non-linear. So we know like what is the linear. Most of these things may be known to you. Okay, but let's try to understand the difference between linear versus non-linear. Maybe few new things might come to you. So we know like when we do linear analysis. Okay, so when there is a linear relationship no, between any input output, right? Between input and output. Okay. So in our case, it's no force and displacement. Okay. Force and displacement. If force is input, you can say displacement is output, and vice versa. If displacement is out input, then we try to find the force. Okay. So in this linear relationship, okay, uh, F is equal to kx. This is not FEA. Just now we are trying to understand with 1D 1D structure. Okay, not FEA, but we can extend this to FE as well. Okay, so when we like first we find no, uh, for given applied load, okay, we find the force, right? We get the force. Okay, and if you want to know the force, I mean if you want to know the displacement for another magnitude of load, okay, then you don't need to do this analysis again. Okay, you can simply use the scale factor. Okay, for this x2 we can need not to find through FEA. Okay, because the relationship is linear. If I say for 10 Newton, if it is a 1 mm displacement, okay, then I can say for 20 Newton it is 2 mm. Okay, you don't need to solve that. So that is linear relationship, and also we can superimpose. Okay, so one thing is that we can simply scale, and other thing is superimpose. Okay, for example, superimpose means like let's know we are doing for load case. Okay, there are two different load cases, load case 1 and load case 2. Okay, maybe this is let's say bending load, and this let's say some torsion. Okay, we are giving some torsion to the shaft. Okay, And if I get displacement here, or I solution, okay, here I get solution for load case 1. Here if I get solution, let's take the d2. D2 means displacement for load case 2, and this is d1. I can, if I want to know the combined effect of load case 1 and load case 2, I can simply no, do summation of this solution. Okay, if I want to know the solution for these two loads together, so that is superimposed. So if I like for FEA, okay, I have this input, okay, maybe force or displacement, okay, and this is output. So displacement or force, okay, F is applied force, okay, applied load. And the relationship we know is K U is equal to F, right? So now in linear analysis, okay, though this relationship is looks direct, okay, the relationship looks direct, but it is not direct relationship, okay, direct relationship, okay, it is not direct. In algebraic equations we say okay there is a direct relationship, but if you closely look at that, okay, it is not direct. For example, uh, it is something like this, okay, we'll take example later, but let's take this is a force, okay, and this is displacement. Force F, displacement U, okay. We know the relationship is direct, okay, that is K, okay, but it is something like this, okay. If you have force, this we are talking about no, 1D, let's take 1D example, let's take uniaxial tension of bar, okay, something like this. Okay, so this is say this is only K, okay. So force is given, okay. If just forget about FEA, if this is given to you, okay, you have area, you have length, and we have also material given. Okay, so these are known things. Okay, if you apply force, what is the first quantity you will find? If you go in a no, simple calculation, okay, from force, okay, we can get stresses, right? I mean, from first force I cannot get the displacement if this is given to me, okay. I get first the stress, okay, and in solid mechanics we have done this, okay, for given force what is the stress, we have found no, learned this, we just simply divide by area, right? So sigma is equal to F by A. From then once you have stress, okay, what is the next quantity that we can find from the stress? Any idea? I know it's simple, but I just want to hear from you.
Strain.
My volume is very low. Okay, can you repeat again?
Height strain.
Yeah, so we can find the strain from material properties, right? And once we have strain, we can easily find the displacement. Okay, so we know the strain displacement relation delta L by L. Let's say delta L. Once we find the display, this one change in displacement, we can find total displacement. Okay, U is L plus delta L. This is how it is, okay, though it looks even in FEA, okay, if you have seen we know like the K matrix, okay. Now let's talk about FEA. Okay, let me put it here. Okay, you have sigma is equal to f by a. We are still talking about this. So this is known. Okay, so sigma is equal to e epsilon, right? And f by a. Okay, from e epsilon I have epsilon's delta L by L, okay, is equal to f by a, and f is equal to a a by L, okay, or yeah, a by L into delta L. Okay, so generally this is what we know, like this is for FEA we have known this equation, right? The for bar element, the K matrix is A by L, okay, 1 minus 1 minus 1 1. Okay, even for this 1D structure, okay, we can directly calculate the displacement from the force. Okay, even if you go this way, okay, but in background there is a relationship between all these quantities, okay, stress, strain, and so you know this f is equal to, here if we see, f is equal to k into x or delta L. This is, so this is u, okay, this is f. So this is what no direct relationship, but in background there is a calculations like stresses and strains are okay, this consists of stress and strain relationship and strain and displacement relationship. Okay, so let's talk about this FEA. So if you understand this, this is very easy, like for FEA. So in FEA, K is equal to this one, and we know K E for element. Okay, stiffness matrix of element that we know, integration over volume, right? B transpose D, okay, B and dV, right? This is in general. If I want to write it for bar element, okay, uh, bar element we know the cross section dimensions are represented as element properties. So the integration is done over length. So L B transpose D B, and this is
The screen is not visible.
Screen sharing has stopped.
oh, okay. So instead of stop sharing, I, instead of hide, I click stop sharing. Okay. So a and dx. Okay. So this is for a bar element. I should have written it here. Anyway, we can write it quickly. So k element is equal to L B transpose D B A dx. So this is kind of revision also is happening. Okay, so here we have seen, no, this is the relationship. We use relation between sigma, epsilon, the D. Okay, then we use a relation between epsilon and U. Okay, which is B matrix. So what I'm trying to say is here, no, we have this sorry, F vector is equal to K matrix. Okay, and U displacement vector. Okay, though we are finding it directly, but in background there are relationship between different other quantities, stresses, strains, and strain displacements. Okay, so what we do, using this we find the U, right? From here we find the U vector displacement, we solve for displacement. Okay, and if you remember, in our steps we have mentioned this. Okay, first thing is find element stiffness matrix. Okay, then assemble. Okay, here before this, okay, how we do this: first find b matrix for each element. Okay, then d matrix. Okay, so it is not for each element but it is problem dependent, so we find sigma epsilon d, like if it is plane stress, plane strain, or 3D. So based on that, d we find. Okay, but b matrix is find, we find for each element. Okay, then we perform assembly, so we find global stiffness matrix. Okay, K. Then third is solve for displacement u. Okay, then so whatever we have done here, b and d, okay, we use the same, then we find the strains. Okay, then we find the stresses. The other things also can be further derived, like for example internal forces or reaction forces at boundary conditions. Okay, so here we find the displacement. Okay, and this little insight we have seen earlier also. So if you see, this is very analogous to our 1D structure. Okay, 1D bar structure that we were talking in earlier slide. Okay, something like this. Okay, now we want to talk about non-linearity. Okay, we take this one. Okay, uh, so I hope you understood this. Okay, this is how it goes. There is a direct. Now all these relations, okay, all these relations valued for certain conditions. Okay, for example, small strains. If we say, okay, we are doing this linear analysis, okay, using this. Okay, uh, but this all remains valid only for some conditions. For example, one is small strains. Okay, other thing is our stresses are beyond, I mean, it is not beyond yield strength. Okay, in case of plasticity. Okay, so under these conditions these are valid. Okay, linear analysis. So why we say like these are valid for linear analysis? Okay, if there are large strains, for okay, let's take there are large strains, then what will happen? Okay, uh, obviously the cross section area, okay, we can say it is decreasing, it will decrease significantly, right? That means, like for example, I have this bar element, okay, or bar structure. Okay, if there is a small strain, okay, okay, from this to this, okay, then we can say the cross section change, okay, cross section area change is negligible, right? And if we have like large strains, okay, then we can, this will not remain valid, right? The cross section area will change. So cross section area decreases significantly. Okay, and also the length also increases significantly. Okay, so when this happens, we have this relationship right here: sigma is equal to f by a. Okay, and epsilon is equal to delta L by L. Okay, so a here this a is not equal to a0, right? And this L is not equal to L0. Okay. So this is like if okay, we are not capturing the transition. If you see this, okay, let me take the linear analysis. Linear analysis is solved in one shot. Okay, so linear analysis, if you have seen in FEA, okay, it is solved in one shot or in one increment. Okay, in FEA terms, okay, in only a single increment. That means we have this particular structure, for example, okay, and this is, let's take a final deformation. Okay, from here to here, okay, we are solving it in one increment, okay, single increment. Okay, but actually to go from here to here, okay, this is undeformed, and this is deformed. To go from here to here, there is no step by step event is happening, you know that it will go something like this. So in linear analysis, we are directly jumping here, okay, from undeformed to deformed position. We solve it in single increment. So what is happening when you do it in a single shot? Okay, we are not capturing actually. We are not capturing the transition. Okay, the transition. This is in. We are not capturing that transition actually. Okay, which is happening from A0 to final A. Okay, A0 to A, okay, and from L0 to L. Okay. So we are not capturing this event, and when we do not capture this, okay, we are not capturing this intermediate, let's say intermediate area and L. That means we are not capturing intermediate deformed positions. Okay, that means we are not capturing instantaneous area and length. Okay, that when we do this, okay, we this will affect the results, okay, like stresses and strains affected, okay? Because we know these stresses and strains are they have area and length. Okay, so this is linear analysis. Okay, in non-linear analysis, so you can understand this is most important characteristic of geometric non-linearity or non-linear analysis. Okay, so in non-linear analysis, one of the important characteristic is that we solve these equations, okay, these algebraic equations, means k u is equal to f. We solve these algebraic equations with respect to deformed with respect to deformed configuration or deformed geometry. Okay, okay, so that is one of the important characteristic of non-linear. So actually what we are doing in linear analysis, we are directly jumping from this undeformed to deformed. Okay, in non-linear analysis, we are actually going in incremental way. Okay, we are going in incremental way. That means we apply only this much load, okay, and try to find the deformed configuration. Okay, then on that deformed configuration, okay, we further apply load and find the next deformed configuration. And once we get the deformed configuration here, we find further load. Okay, we increase the load, then we find the next deformed configuration. So when we do this incremental way, okay, we are actually capturing the, okay, we are actually capturing that transition. or I would say capturing the deformed position. So this is a main characteristic of nonlinear analysis. Okay, if no simple takeaway is that it is solved in incremental way. So I'll just highlight this. So all the nonlinear analyses are solved in an incremental way. Reason is simple, that we want to capture something which is happening in between. Okay, and that is the reason we go non sorry incremental way. Okay, so we talked about this one. And yeah, so we said like valid remains linear analysis remains valid in small strains that we have discussed, like large strains. What is the effect of large strains? Now, when the stresses are less than yield strength. Okay. So the second is first we discussed small strains. Okay. Then second is stresses less than yield strength. So these are two conditions for our linear analysis. So now this is also very clear. Okay, when stresses, if what if stresses are no stresses are more than yield strength. Okay, uh, so this is particularly, we know, like yield strength is in case of elastoplastic materials. This is one of the non-linear material. So let's talk about like this elasto elastoplastic, okay, yield strength. So in that case, what happens? Our this event also we are not capturing. So beyond yield strength, we know there is no linear relationship. Okay, no linear relation between sigma and epsilon. Okay, so it is not a proportional or linear relationship. That means there is a non-linear relationship, and this is also linear and reversible. The linear analysis, we assume that it is linear relationship and also reversible, but in non-linear analysis, the relationship is non-linear, okay, and irreversible, like in case of elastic plastic. So when there is something like relationship is changing, so as you know, as we can understand in the same way, okay, we are not actually finding the stresses. I mean, when we are solving with a single equation or single increment, we cannot capture that change, okay, which is happening between sigma and epsilon. And that is the reason we need to go for incremental. So these are the some reason, I mean, something incremental, why there is an incremental method. Okay.
Vivek ji, can you repeat once again?
From where? From this
Yeah, the last one which you told.
this one.
Yeah.
Okay.
Nonlinear irreversible.
You are saying this non-linear and irreversible, right?
Yes, sir.
No, so I'm just giving example now. Anyways, this we will see in our module number 4. Okay, non-linear material. But I'm just giving example. First condition is small strain. Okay, no, for which the linear analysis is valid. The second is when the stresses developed in analysis. Okay, if they are less than yield strength of the material. Okay, so this is one example I'm taking. Okay, this is not true for hyperelastic. You know, hyperelastic doesn't have any yield strength. Okay, but let's try to understand it with the elastic or metal plasticity. So when stresses are less than yield strength, okay, sigma is equal to E epsilon. We know this. Okay, but that means sigma is proportional to epsilon. There is a linear. This is linear relationship. uh, for less than yield strength. Okay, but once we cross the yield strength, okay, the sigma not proportional to epsilon. Okay, we know this for metal plasticity. So this is the, sorry, this is a linear relationship. Okay, this is our yield strength. Okay, this is sigma epsilon. So this is for linear analysis, this region. Okay, but beyond yield strength, the sigma epsilon relationship is not linear. Okay, so this is linear and this is non-linear relationship. Okay. So sigma we can say is a function of epsilon, which is non-linear function. Okay, so what I am saying here, when we solve it with a single increment, okay, for example in linear analysis we simply solve the entire equation or solution. There is a single increment or one shot there is a solution. Okay, when you do that, okay, uh, for example here, okay, I think we have taken this. Okay, let me write it here again. Okay, this is my undeformed position. Undeformed, and let's take this is a deformed position. Okay. And I'm saying that in case of linear analysis, okay, this is the solution. Okay, you have undeformed and deformed. You solve this you solve this equation, okay, in one shot. Okay. So when there was undeformed position, okay, we know we have taken sigma is equal to E epsilon, right? So if you solve it in one shot, okay, from here to here, we directly get the solution. What is happening in between, okay, in the intermediate, there might be something happening, right? For example, we said area change, length change. Similarly in uh, nonlinear material case, intermediate, that something is happening. For example, the stresses are more than yield strength. Okay, if this is the case, if this is happening in between, how do we capture this intermediate? Okay, we cannot capture with linear analysis because we are solving it in one shot or one increment. Okay, for example here, state, this state, okay, and this state, these intermediate transitions we are not able to capture in terms of stresses and strains, or also in terms of geometric changes. Okay, that might happen like, okay, you apply let's say 10 newton here, sorry, axial load. Okay, 10 newton you are applying all together. Okay, and you get this displacement, let's take 10 mm in linear analysis. It may happen that no, when you do this solution, uh, here maybe somewhere here you get some plasticity. Okay, your stresses might be more than yield stress. Okay, so that you are not capturing. That is what I am trying to, put the point here. Okay, is it clear? I mean, it's straightforward. Okay, there is nothing much complexity here. Okay, so
Sir, can you
yeah.
hello? Sir, can you give me any example related to non-linear analysis? Sir? Where what will be the use case in that non-linear?
Okay, so there are so many examples. Okay, so as I said, no, we will uh, talk about these examples. I mean, from here there are only examples of non-linearity, so don't worry. Right now we are just no trying to understand the nonlinear analysis and Newton-Raphson method. This one, okay? How to solve the nonlinear analysis? We'll see like what are the different nonlinear examples. But let's try to understand like how to solve the nonlinear analysis first. So
Okay.
there are, you take all the examples, most of these applications in automotive or in any metal forming. These are all non-linear. Okay, if you just asked, so let me give some. examples. Okay, the rubber, okay, tires, tire analysis where you have rubbers. Okay, those are hyperelastic material. Those are hyperelastic material. So this is a sigma epsilon. Okay, which is something like this. Okay, so this is non-linear relationship. Sigma and epsilon is not proportional, or there is no linear relationship. Okay, then contact. Okay, contact we will discuss. Contact is type of non-linearity. Then you take any plasticity problem where the stress is more than yield strength, that is a non-linear analysis. Okay, like in metal forming and different forging applications, all those undergo plastic deformation, so that is non-linear analysis. Then you have buckling problems. Okay, like you have constraint here and you are applying some force here. Okay, uh, there there is a buckling happening. Okay, so this is also non-linear. Okay, because there is a larger strains and large, sorry, not large strain, but large displacements and rotations. So we will see these different types of non-linearity as and when we discuss about this complete module 3, 4, 5. These are all non-linearity, so we'll discuss one by one. Okay, uh, linear and non-linear. Okay, so when we talked about small strains, okay, then we go for linear analysis. For non-linear analysis, it's a reverse. Okay, it's large strains, and also they call finite strains. Okay. Then we have not discussed about this particular thing, that is small displacement. Okay. But we'll discuss this later. Okay, so we have not reached to that section of geometric non-linearity. Okay, there we will discuss this. And this is large displacement. Then small rotations, we'll again recap this everything. The small displacement, or sorry, large displacement and large rotation. Here large rotation. Okay, what else can be is like your contacts. Okay, so there are two components interacting. This is also non-linear. So any one of this is present in your model, or you are expecting any one of this in your physical behavior. Okay, then you have to do non-linear analysis. Okay, any one is present. Okay, so let's move to the non-linear analysis. Okay, how to solve that. Okay, so no, no, non-linear. So we need to first capture that event. Okay, that is changing. Okay, we have to capture that event. Capture the event change. Okay, as we increase the load. Okay, as we increase the load. So here events can be anything. Okay, as mentioned here, one is the small strain. There can be large displacement also happening. Okay, like this is a, we can say if this is undeformed. Okay, and this is small strain. Okay, this is small strain because there is very small change in. I mean, strains are very small, uh, but this can all be large displacement as well. Okay, because the earlier the position was here. Okay, let's say 0 0. Now it is at no, this position is, let's say, 10 0. Okay, the strains are small but displacement is very large. Okay, it has moved to this displacement, to this position as well. Okay, so this is a small strain, large displacement, large displacement. Okay, there can be large rotation as well. Okay, let's say there is from here. Okay, uh, there is a rotation as well. The strains are still small. Okay, like small strains, but the rotations are large. Okay, so that is large rotation, small strain problems. And there are so many applications, I mean examples, real examples for this. So this when we are saying like we want to capture that change in event, that means not only large strain, but we are also saying large displacement and large rotation. Okay, so here like all large strains, okay, and large displacement and rotations. Okay, that means we, as we said, like we need to solve the system in incremental way. Okay, or step by step in level. It's a step by step. Okay, so this is the main concept of nonlinear, solving the nonlinear equations. Okay, now let's take see example. Tomorrow I will take real hand calculations, but today no. So tomorrow what we will discuss, like we'll see some geometric nonlinearities, some demos, okay, some introduction of geometric nonlinearities, some small theories on concepts. Then we'll see some demos of geometric nonlinearities. But before going into that, okay, we'll see this Newton-Raphson method. Okay, so today let's try to understand how this works. Okay, and tomorrow I think we have half an hour. So tomorrow what we will do, today we'll just understand how this method works. Tomorrow we'll take actual 1D bar element, okay, FEA. Okay, and uh, we'll try to understand this Newton-Raphson method with hand calculations. Okay, this is for tomorrow. So actual calculations we'll do tomorrow. Let's overview or conceptually understand Newton-Raphson method. Once this is clear, then we can easily understand these hand calculations tomorrow. Okay. So I'll take a simple example. Okay. No dimensions, nothing. Okay. Values, just example. Okay. So let's take, this is our structure. Okay. And we know we can represent. Let's take we are modeling, we cannot represent always, but let's take we are modeling this structure as a 1D. Okay, as usual, like in earlier cases, like in module 1 we have tried to understand this everything with 1D. So let's take this way. Okay, this is 1D bar element, we are modeling it with 1D bar element, uh, which has two nodes, node number 1 and node number 2. Okay. So what is known? The force is known, right? External load, let's denote it as a P. Okay, P is applied load or external load, okay, or external force. And what else is known is this area. Okay, initial area, okay, initial length, and Young's modulus. Okay, this is known. Okay, so as I said, now we want to find the what is a linear analysis. It's simple. Okay, P is equal to Kx. Okay, P vector or F vector. Now I am denoting it as a P. Okay, so this is same what we said. No, F vector. Okay, but let's put it as P for now. Okay, P is equal to K. This is for element. Since our element, I mean our global system has only one element, so this is also global equations. Okay, we simply put no k values and p values, known values, and find the displacement. Okay, that is linear analysis. We apply full load, okay, in linear analysis. But as we said, like we want to do it incrementally. That is our non-linear analysis. Okay, so I want to draw the straight line. Okay, so this is, so let's take this is the applied force P, okay, and this is a displacement. Okay, so this is linear. Uh, we know this one. Okay, we have applied force P and we know the K, and we simply found the U displacement. Okay, but non-linear analysis, this one is not known, right? I mean, we know, like let's say this is a expected non-linear response. Okay, let's check this is expected non-linear response. Okay, please note that this is not known. Do we know, like, no, for given load P, okay, this is my displacement. Okay? This is not known. Okay, we want to actually trace this curve. Okay, so this is not known in advance. Okay, so we'll see like what is known in it at the first place. Okay, so we want to trace this curve. So as I said, we'll go by incrementally. Incrementally means let's take increment 1. Okay, increment 1 means applied the load incrementally. So let's take first load increment. Okay, if this is just for example, let's say you are applying full 10 Newton load. Okay, so we'll take load increment for in first increment, that may be 5 Newton. Okay, P1. So let's take load increment for increment 1 is P1. Okay, this is known. Okay, we are applying only, let's say, half load. Okay, that can be anything. Just for now, assume that we are applying half load, whether half load or 20 percentage load or whatever, that we'll discuss later. But let's take we are solving this problem with two increments. Okay, let's take two increments we are solving. That means in first increment we'll apply 5 Newton, and second increment another 5 Newton. Okay, so this is my 5 Newton, that is P1. Okay, so I have P1 known. Okay, load increment at increment 1. What else is known? Any guess?
Stress, sir.
What is it?
Stress.
Stress is not known, right?
As a K is known.
Thickness.
Slope.
Okay, you are talking about that. Okay, 1D structure. Okay, this one we have just talked this 1D structure. Okay, so we are not now talking about this 1D structure. Okay, we are talking about FEA now. Okay, this one. So we are not talking this one. Okay, like from force you directly find the stress. Okay? That is just for explanation. Okay, uh, I have taken this example. Okay? But in FEA, you don't find the stress at the first, right? We have discussed the steps of FEA also, right? These are the steps of FEA. Okay? We find the stresses as a derived quantities. The primary solution is displacement. Okay, stress and strains are derived quantities. So okay, just think about FEA now. Okay, uh, like we have this P. Okay, now let's say P1 is equal to K E. Okay, at increment 1. Okay, let's say K1 and U. Okay, so now what is known here? P1 is known, right? Then what else is known? K, right? K for this we are talking about bar element, this one. Okay, A0 L0 E, and this is finite element now. So K at initial position is known, right? A0 A by L0, right? Okay, so this is known. Okay, so P1 and K1, this one means increment 1. Okay, sorry, this is P1 and this one is for iteration 1. Okay, so now increment 1, this K matrix is known. So let's say this P is known here, this value is known. And what is known? So this is known, right? This is K at 1. Okay, initially this is known. Hope you are getting this, right? The initial stiffness of the structure is known because we know the initial geometry and E, all these parameters are known. So what we have is load is given, that is input, and K is known, okay, from the undeformed position. Okay, so from this and this, okay, I can find this slope is known and this value is y-axis is known. Okay, so I can find this delta in x-axis. Okay, this is known. We can find this one. Okay, let's take this is u1. We can find from this our displacements, right? U is solve for ue. Actually, if we take this example, okay, we are talking about 1D structure, sorry, 1D bar element. Okay, this is 1 and node 2. So this is already constrained, so we are actually solving for u2. Okay, so we solve for UE, vector UE, right? So U1 and U2 are known from this. Okay, this is now as per linear analysis what we do. Okay, simply put the boundary conditions, loads. Okay, instead of full load, I am applying just half load. Can find the displacement. Okay, now this is what this solution I have got here. This one is actually linear solution, right? Okay, but actual nonlinear analysis, the actual response is this one, right? This is unknown. Okay, note that this is unknown for now. Okay, we want to find this point, but we found this point actually. Okay, displacement u for this one. Okay, so this is wrong actually. For this load I'm getting this displacement, but actually for this load I should get this displacement, right? Okay, uh, so what I am doing, I am tracing this curve now. Okay, just hold on for some time, you will understand. Okay, let's check iteration 1. Okay, so I am doing iterations now. Okay, so I have u1 and u2 known. Okay, this way x-axis is known, so I need to find this point. So what is this point? Any guess here? What is this point? This is first of all unknown solution, right? Okay, but there is some characteristic of this unknown response. Okay, for this displacement, okay, there is always some this is like when we apply external forces, okay, the body is generating internal stresses, okay, which will in turn generate the internal forces. Okay, so for that given external force there is an internal force. Okay, and for this external force, okay, we need to find the internal force.
Maybe it's like reaction force.
Okay, not in this case we can say yes reaction force for this case, but in general FEA the reaction forces are different and internal forces are different. Okay, reaction forces you will get only where there is a boundary condition, okay, like where you fix the constraint. Okay, internal forces you will get for all the elements, okay, irrespective of whether boundary conditions are given or not, because when we have this structure, okay, you have elements. Okay, when we apply force, okay, it will undergo some displacement. Okay, so there is some stresses and strains here. Okay, these stresses are called internal stresses, you know that. Okay, so these internal stresses will generate the internal forces. Okay, internal forces. And the condition for no this deformed configuration is that external forces should balance the internal forces. Okay, this is the condition, right? So for this given external force, okay, which generates internal forces, they both should be equilibrium, and that is our this response, okay, unknown response.
Sir, I have a doubt.
Yeah.
Sir, because of these internal forces, will the body act like as a rigid body?
No, internal forces are like, for example, you are stretching it. Okay, it has undergone some stretching. Okay, so there will be some stresses and there will be internal forces which body will resist, right? Stresses are nothing but resistance to the external.
Yeah, so it will resist the external load, right?
Yes, so it will resist the
So,
internal forces will resist the external force. That means both should be in equilibrium. Okay, both should be equal, right? The external
yes.
forces should be equal to internal forces. That's how we can say like, okay, the body is in equilibrium. Okay,
Okay.
so if I say like 10 newton I am giving external force, and due to stresses if it is generating only 5 newton internal forces, it is not correct. Okay, if I have
Yes, the body will be moving with 5 Newton force because
yeah,
of that 5 Newton force.
I mean, it is like what
Okay.
we are giving, we should get that. Okay, so 10 newton means
Okay.
from internal resistance I should get 10 newton only internal forces. Okay,
Okay.
so
Like to be in the stable equilibrium.
yes, 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 exactly. So
O-
this unknown
Okay.
nonlinear response is actually equilibrium curve.
Okay.
Okay, so what is equilibrium means external forces are equal to internal forces. Okay, P is equal to I. So this curve is the characteristic of this curve is P is equal to I. Okay, so we don't know this curve, but we know like on this curve there is a external forces and internal forces should be balanced. Okay, okay, so let me take that one again. Okay, the page is very small. I mean, I can draw small also and try to explain, but it will be confused, so I have draw it bigger. Okay, so I have put.
Sir, like you have drawn that curve, right?
Hmm,
So,
yes.
like, what is the equation of that curve? Like, is it? Uh,
Okay,
uh,
this is unknown. Okay, note
yeah.
that this is unknown. Okay, there is no equation of this. Okay, just don't say like P is equal to no k u square like that. Don't think about this. Okay, this is for 1D structure we talk about. Okay.
So, is it representing like points joined at the like different instance of time?
Mm, okay, uh, So what this represents is, for this example what I have taken here, okay, P, okay, this is fixed, node 1 is fixed, okay. So I want to find the u2, right? u1 is 0, u2 is what I need to find, okay. So this is, let's say this has stretched something like this, so this is u2, some value, okay. This is unknown, so this, on x-axis I am actually talking about u2, node 2, okay. And this is external force P, which is applied at node 2, okay. So force versus displacement, that is my nonlinear, that is my response that I want to find. Is that your question? What is this curve means? I mean,
Like my question is that how we got that behavior of the curve. Actually, how do we get that?
that's what I
Like
said.
from
We have not got this curve. This response is unknown.
okay,
We are saying like this. This is supposed to be response, okay, but it is unknown.
okay,
Okay, let's
okay.
take. We have given 10 Newton here. Okay, the actual the idea. I mean, the real output is, let's say, 5 mm. So I want to
And then why will not it be linear? Like
exactly. So
will
that's
it be
why I said,
linear?
uh, okay, if you give, if you apply 10 Newton, okay, the non-linear output is 5 mm, okay. I cannot just simply put 10 Newton and find the 5 mm, okay, from this equation, okay. K u is equal to P, okay. I cannot get this because the K is, when I use this I get this output, right? This is linear, this is linear, right?
Yes, sir.
Okay, so when you, at the first, when you solve this equation you get this output, because, okay, so you get this one,
Okay.
okay. So this is where we want to go actually, but we get this one, okay. This is for iteration 1,
Okay.
okay. For iteration 1, what we have discussed is iteration 1, okay. I am giving, let's take full load, I am applying, okay. Let's take full load, okay. P1 is equal to 10 Newton. I have K, okay, for iteration 1, which is known, okay. Then I can find u2, sorry, u1 at node 2. This is for iteration, okay. Subscript is for iteration. So 1 is equal to, let's take some value, okay, this one. This is u at iteration 1 for node 2, okay. I got this value, okay. So from this one, okay, can I, what is, I want to find this point, okay. So how we get this point? From u I can find the strains, as usual, the same procedure which we follow in FEA, okay. I can get the strains for that element, right? For 1D element, this one, what is that? Epsilon E is equal to epsilon xx for 1D, which is b b vector in u, which is u2 minus u1 by L. You can review this in our old notes, okay. Tomorrow I will show this with a calculation, but this is how we find, okay, u2 minus u1 by L, okay. So we get, once displacement is known, strains are known, right? Once strains are known, stresses are known, correct? Okay. So in
Yes,
iteration one,
sir.
what we are doing, we are actually doing linear analysis and finding all the quantities. Okay, just remember that. Okay,
Okay.
there might be some doubts. Okay, don't worry. At the end of this complete, you will get all the clarification, because we have not completed now. So there will be definitely some doubts. Hold on for some time. Okay. Now this is done. Okay, now I want to find this point. As I said, this is the equilibrium point. Okay, this which is not known, but we know at this point external forces P and internal forces are same. Okay, so from this sigma, okay, internal stress, I can find internal forces. Okay, I at iteration 1. Okay, for one d, let's say no, it is, this is 1d case, so we can find I1 is equal to sigma. This sigma e is nothing actually sigma 1 1. Okay, or sigma x for 1d case. Okay, so I1 is equal to sigma x divided by area, right? So I can find the internal forces, okay, in that bar element, bar finite element. Okay, so I have external force P1 and internal force I1. Okay, when you find this from this stress, no, it will be this point actually. This is actually your I1. Okay, though you apply 10 Newton, I1 you might get, let's take 7 Newton. Okay, and so what we do, external force is applied, we get the internal forces. Now we say, okay, external forces should be internal forces. Okay, but it is not the case. Okay, so what we get some residual R1. Okay, at iteration 1 we get residual minus I1. A residual means kind of error. Okay, residual force, it is called residual force, or error in that iteration. Okay, so we get this value. This is P1. Okay, this is I1, so we get this as a R1. Okay, so it is simple. Okay, just external force is applied, you got the displacement. From displacement you get the strains. From strains you get the stresses. Same FEA procedure. From stresses you get the internal forces. Okay, this, when you get these internal forces, that point is actually this. So actually what we do, we go like this, then we come here, this point. Okay, we have, these points are known, this, okay, A and B points are known. Okay, the slope and load, so we get this C point. Okay, when we follow this procedure FEA, further after solution U, we follow this FEA steps, we get I. Okay, so from C we get this D point. Okay, so once we get the D points, we can easily find what is the error between this external and internal forces. Okay, that is R1 is equal to P1 minus I1. So this is for iteration 1. When we say like, okay, P1 minus or R1 is not equal to 0. Okay, for now let's say 0. It should be 0, right? P1 is equal to I1. It should, equilibrium means P1 should be equal to I1. Okay, so when we take the difference, we get some error. Okay, that is not 0. That means we say iteration 1 is not converged. Okay, because you have got some error. Now when this is not converged, the Newton-Raphson method, it will continue with second iteration. Okay, put this as a different color because iteration is not converged. Okay, because the residual is not 0, so it will move to iteration 2. Okay, so in iteration 2 we follow the same procedure. What is known, R1 is known, that means this load is known. Okay, this much is known. Okay, then what else is known, we are at this point. So at this point we get the new stiffness, right? Like this. This is K1, iteration 1. This is stiffness matrix at K2. Okay, so R1 is known, K stiffness matrix at iteration 2 is known because we know new deform configuration at the end of iteration 1. The new deform configuration is, we have all the displacements, right? Stresses and strains, so displacement is known, so we know the new deform configuration at this point. point D. Okay, that is coming from iteration 1. Okay, so new stiffness matrix, which is AE by L, okay, for this bar element, okay, we can find. Okay, so it is called updating the stiffness matrix, or we say update stiffness matrix. Okay, so actually this is stiffness matrix, but in nonlinear, because we are updating it, it is called tangent matrix, because it is changing. It's the tangent actually. Okay, because now A is known, okay, new deform configuration A and L is known, new length, new area is known, E is not changing. Let's take, now it's a, we are taking only nonlinear geometry. E is not changing. Even if it is changing, we can update it here. Okay, AE by L. So new stiffness matrix is known from the instantaneous area and instantaneous length. Okay, so what I'm saying, yeah, R1 known, K2 is known. Okay, this K2 is known, this error is known. So u, we can find, right, u easily from this, right? Now here what it will solve, okay, uh, K iteration 2 u e, okay, for iteration 2 is equal to, can you tell me what is the right side term? Here we were saying it is K iteration 1 u iteration 1 is equal to external force in iteration 1. Okay, so what is the right hand side here? Any guess?
P2.
Residual.
L1.
It is R2, R1. Okay,
Yes.
the residual, okay, will become the external force here now, because this is known, right? Okay, if you have K2 here, let's say K2 is known, and if you take P1, okay, K2 is actually slope between R1 and this difference, right? If you see K2 is the slope, okay, it is a slope between R1 and this new displacement increment, okay, these two. So not P1, but we have to take R1. Then, so this is known. If we take R1, we can find this value. Okay, so if you take P1, it is again different thing. Okay, uh, so we have to take R1. Okay, this point we have already got, no? Now we need to find this point. So this much I have to find, which will come from R1 and K2. Okay, hope this is clear, right? This is clear, I'm assuming it is clear to everyone. Okay, so from this it is simple. Okay, just what we are doing, we are updating the stiffness matrix, which is called tangent matrix now. Okay, and the force will be R1 now. Okay, so from this we can solve for our unknown displacement u, right, at iteration 2. Okay, so this is known now. Okay, after we solve, this is known, okay, this value. Okay, so what we do actually, the previous iteration and this one we combine, we get total displacement. Okay, so, and this is called actually increment, displacement increment. This is called displacement increment. Okay, when you sum all the previous iterations displacement increments, you get total displacement. Okay, anyways, so we got this point. Okay, u2. Okay, okay, can you tell me what next after we get u2? Same procedure. Okay, here what we have done, so once we have displacements, okay, we get the strains, right, for iteration 2. Once we have strains, we can get the stresses for iteration 2. Okay, now we want to find this point. Okay, I'll take another color. I want to find this point. Okay, So from sigma internal stresses I can find internal forces, right, at the iteration 2, which is nothing but this point. Okay, this point. So it is same. Okay, I am going from point A to B. So sorry, A and B points are known. I get the C point. Okay, I follow the FEA steps. Okay, then I get the D point, which is internal force. Okay, similarly here I have D point known now for iteration 2, and E point is also known. Okay, because R1 is known and K is known, so this D and E is known at the start of iteration 2. Okay, so from E I get this F. Okay, due displacement. From F, okay, I get this I calculate the internal forces, so I get this G point, right? So it is, you are going like you are coming down and going up. Okay, to find the equilibrium point. Okay. So this G point is nothing but I2. As we told, the characteristic of this unknown nonlinear response is that it is in external force is equal to internal force. Okay, so this I2 is known now. Okay, this is now I2. I2 is this one total. Okay, this is I1. This is I2. So again, once I2 is known, okay, what is that we have to do? We have to check the equilibrium. Okay, as we did in equilibrium. We did this in iteration 1. So how we check the equilibrium? We know the external force. Okay, now you have to compare. Here we have used R1, but the equilibrium when we check, we have to see P1. Okay, P1, because external force total applied is P1. Okay. For this iteration it is R1, okay, in order to find the displacement increment. But when we uh, check the equilibrium, it is P1, okay, should be equal to I2, right? Because we have applied total P1, right? Okay, so we have to check P1 should be is equal to I2 in equilibrium. Okay, so obviously it looks like no, they both are not same. P1 is here and I2 is here, so we say R2, there is some error between external force and internal force. Okay, which is not equal to 0. Okay, so we say like this iteration 2 is also not converged. When it is not converged, so the Newton-Raphson method will continue with iteration 3. So iteration 3, I think I am expecting from you, like, no, you tell me the procedure. Okay, so here this iteration 3, we are at this point. Okay, deform configuration from iteration 2 is known. Okay, so what is known here? R2, right? R2 is nothing but P1 minus I2. So this R2 is known. Let me zoom it here. Okay, let's take we are at this point, so I am just enlarging this one. Okay, this is at the end of this is I2. Okay, let's say this is P1, and yeah, so R2 is known, right? So R2 is given or known from the previous iteration. What is known now, or what we have to update now? It in iteration 3,
Stiffness math.
stiffness. Yeah. So this new deformed configuration is known. Okay, we have this displacements. Okay, U at iteration 2. That means we have new deformed configuration, like new uh, length and area. Okay. So we go no, we have this so we can easily find K. Okay, we have to update the stiffness matrix. Okay, which is A I E by Li. Okay, now this AI and Li is now from this configuration. Okay, Previously it was from here. Now this is new configuration, so instantaneous area and length will change. Okay. Okay, so this is known now, right? This is nothing but k3. Okay, k at iteration 3. So r2 is from previous increment, k need to be updated, so k3 is, we can find k3. Okay, so from this y and this slope I can find this x. Actually in graph it looks like slope, but actually we solve the equation. Okay, that is k, sorry, k matrix, k at iteration 3, displacement vector at iteration 3 is equal to, what is the external force now for iteration 3?
R2.
R2. So we solve for this. Okay, but to understand we are just saying this is slope, this is given, so we can find this value. Okay, but actually in FEA this is what happens. Okay, so k3 is known, so we find the u3. Okay, so once displacements are known, what this point is known, right? This delta u, which is called displacement increment. Total u3 is equal to u2 plus delta u. Okay, from previous iterations we have to sum the displacement. So this is total displacement at iteration 3. Okay. So u3 is known. Okay, from u3 what is the next? Force p is given, force P is there, external force is there, we have found the displacement, we have to find now this internal force, okay, to check the equilibrium. So we have to find this point. Okay, so from u3 again we find the epsilon 3. Okay, strains, then from strains we find the stresses. Okay, then from stresses we find the internal forces. Okay, I3. When we find this, as we said, it will be always this point. Okay, when you find the internal force you get this value. Okay, I3. Okay, so now we have to check equilibrium. Okay, check equilibrium, how to check the total external force P1. Okay, whether is equal to I3 or not. So they are not equal, so there is a residual which is in iteration 3. Okay, now I'll go back to here. Okay, this is my iteration 3. Okay, hope you are able to see this. Okay, and I get this value. Okay, this is my u3. When I get u3, this is my, hope you are able to see, right guys? Okay, I don't want to put it here. Okay, this one. Okay, not the enlarged one but here only. Okay, so this is our I1. Okay, which is very close to P1. Okay, this is P1 and this is my I3. This is I3 and this is my P1. Okay, now we get this residual as R3 because there is an error between P1 minus I3. Okay, so what I am saying here in iteration 3, okay, there is a residual R3. If you continue with iteration 4, will you be able to say like R4 equal to 0? Okay, if you see that, okay, when you zoom this, okay, there is always some error. Okay, so r is never 0. Okay, will never be 0 numerically. Okay, value, uh, because there is always small error. Okay, maybe let's take, if I give 10 newton, the r may be like 0.1 newton in iteration 3. In iteration 4 you may say like, okay, 0.005 newton. Okay, in iteration 4. And you are continuing iteration 5, you are saying like, okay, now error is 1 e minus 6 newton. Okay, but if you see, since this is a non-linear, it is never 0. Okay, iteration 5, this is never 0, so r is never equal to 0. So we have to stop somewhere. Okay, we cannot say okay, I'll keep continuing doing these iterations like 10 raised to minus 6 Newton error, then we have to say something we have to stop something saying that this error is acceptable to me. Okay, so we have to say like r is never equal to 0, so we have to say residual air force, okay, or error should be less than equal to some tolerance. Okay, that tolerance we have to specify. Okay, because we know the residual force can never be 0, so we are saying okay, stop the iteration when it meets some tolerance, and the smaller tolerance is very small. Okay, so when we say okay, in iteration 4, when we are doing iteration 4, okay, my residual force is less than r4 is less than is not equal to 0, but it is less than or equal to some tolerance. Okay, this we will talk later tomorrow. Okay, when it is satisfying, and let's say iteration for it is satisfying, we say this increment is converged, this complete increment p1, okay, is converged. Okay, okay, we'll stop here. Okay, but tomorrow we'll repeat, not repeat, but quickly we'll go over this recap this Newton-Raphson method, and I think tomorrow it will be more clear, but I'm just want to know if you are able to follow this procedure, Newton-Raphson method. Okay,
Yes, sir.
okay, great. Sai, Teja, you are saying okay. Any others, are you able to follow this procedure?
Oh, yes, sir.
Yes,
Yes, sir.
yes.
Yes, sir.
Okay, great to know that. Okay, so what we'll do tomorrow, okay, I'll recap this thing. Okay, and
Okay.
we'll take example of 1D bar element same. Okay, but we'll take values, we'll take a, l, and e. Okay, then these 3 4 iterations we'll do with the hand calculations. Okay, we may use excel, or you can use calculator and let me know. I'll try to do it in prior in my notes. If not, then please help me tomorrow with some calculations, but I'll try to do it beforehand. Okay, right, my screen.
Yes.
So
Yes, sir.
yeah, so this Newton-Raphson method. So when you go online, no, you will find Newton-Raphson method in mathematical equations and all. They are little difficult to understand. Okay, but with this it will be easy to understand. So Newton-Raphson method is called incremental iterative method. Incremental iterative method. Okay, so I'll just summarize why incremental. Uh, Now we have taken full load. Okay, but let's take you take P1 is equal to 5 Newton. Okay, then you perform some iterations and make it converge. Okay, then you can take P2 is equal to another 5 Newton. Okay, then you can say let's converge it with some iterations. Okay, so this is in incremental I am solving. I am applying load increments. Okay, load increments. Okay, why iterative? For given load increment, let's say P1 equal to 5 Newton, I have to check whether the deformed configuration is in equilibrium or not. Okay, whatever internal forces I am getting, whether they are balancing the external forces or not. Okay, so to check that, we perform iterations. Okay, so within increment there will be iterations. It's like load increment. Okay, within each load increment there will be iterations to check equilibrium. Okay, so once this load increment p1 is converged, okay, with let's say certain number of iterations 4. Okay, then we move on to next load increment. Okay, load increment. This is load increment 1, this is load increment 2, which is P2. Again for P2, we check the same way. Okay, we perform the iterations to check the equilibrium. Okay, check equilibrium with iterations. Okay, and that is how it is called incremental iterative method. Okay, solve with so many increments, and each increment perform iterations to see whether increment is converged or not, or check the equilibrium. Okay, so and it is not always you might have asked questions. Okay, I have full 10 Newton load. Okay, how should I go, whether 5 Newton plus 5 Newton, or let's say 2.5 Newton plus 2.5 Newton, okay, plus 5 Newton, like this. Three here, two increments, here I have three increments, or let's take four increments, four number of load increments, or 10 Newton altogether. Okay, only one increment. Whatever you do, everything is okay. Okay, only thing is that the load has to be in equilibrium with internal force. Okay, so in this is also called implicit method. Okay, Newton-Raphson is actually implicit method. There are two FEA methods. One is implicit method to solve nonlinear solution. Another is explicit. So in implicit, they always do Newton-Raphson. We are not going into explicit, but in implicit method, when you perform nonlinear static analysis, okay, in Abacus or any software, in the background it runs Newton-Raphson method. And you know, nonlinear static is implicit method. When you take Abacus or ANSYS, it is an implicit method, and in that it is in a solver it runs Newton-Raphson method. Okay, so now it is clear. Okay, now you should not have question. Okay, I should apply 10 Newton in the first increment, or should I apply 2 Newton in the first increment? It doesn't matter. Okay, anyways we are going to check the equilibrium. Okay, it will check, Newton-Raphson will check the equilibrium for any load you apply. Okay, so solution will remain same. Okay, you solve with this method. Okay, so sorry, with these two increments you get, let's take 5 mm. Okay, you apply three increments, at the end of solution you get 5 mm. You solve with four increments, there also you will get 5 mm. And here, even if you apply 10 Newton all together and perform iterations, you will get 5 mm only, because the Newton-Raphson method is checking the equilibrium. So your output is a unique output. Okay, it doesn't matter whether you solve with 4 or 5 increments. Okay, so I think I missed this to summarize like iterative methods, so I had to extend again. Anyways, so tomorrow we will see. Okay, okay guys, if you have no questions, we can disconnect and we'll meet tomorrow same time. Okay, I'll send the invite. Okay, tomorrow.
Okay, sir. Thank you very much.
Thanks.
Thank you, Vivek
Thank
ji.
you, sir. Bye.
Welcome.